Storms caused by updrafts. They've become something of a special interest to NASA. In fact, it has a special program called the Investigation of Convective Updrafts, or INCUS. And it's made some awards recently to launch measurement satellites. Joining me with an update, the manager of NASA's weather program, Will McCarty. Dr. McCarty, good to have you with us.
Hi, glad to be here.
Well, tell us about the INCUS program. This is a special kind of storm. I guess we've all seen them with like really tall, towering clouds. What is it you're trying to do here with this program?
Yeah, so one of the really neat things about INCUS is from space, we've been able to look at these types of clouds. So they're big, they're, these really deep convective updrafts. If you see like a severe storm, looking out the window and you see a big, tall cloud in the distance, that's a strong convective updraft. So we've seen the pictures of them when we've had satellites go over or ground radars look at them at an instantaneous time. But really from space, what we've never been able to do is watch them grow and see how they change in time. So what's different about INCUS than other radars we put into space is we're actually launching 3 on the same rocket, and we're going to fly them in different time separations so that we can actually take a sequence of pictures instead of one picture. So it's the same thing as like a flip book where you can look at the 3 different pictures and get an idea of how they're changing over shorter time periods. And that gives us an idea of how they're growing, how they're intensifying, or in some cases, how they're dying out. But fundamentally, it gives us an idea of really the dynamic motions within the storm, not just the picture of what the storm looks like at an instantaneous time.
Right. And when you say looking at them, you don't mean from a visual sense, but from a measurement of atmospheric phenomena, or also
right.
How they look?
Yeah, so a little bit of both. We have one of the satellites has what's called a microwave imager, which really looks at the structures of the precipitation in the storm. So it gives us a spatial map. It's not like what you would see on your eye with your eyes, or what you would see on the news of the satellite hurricanes going over that look really visually like clouds do. This is using emissions from within the clouds that are really a function of the deep rain in that cloud. So that gives you an idea of the spatial picture, and we have one of those. But what we also have are 3 radars. So these radars send a pulse down, and those pulses basically bounce off of the precipitation within the storm and come back, just like a ground radar does and the weather radar you see on the news. But this is doing it from space, basically, and that gives us not just a picture of the storm on a 2-dimensional flat basis, but it really gives us that vertical profile within the storm of what the structure looks like internally. So with that, you can basically see with those 3 radars then, we get an idea of not just what the storm's changing on any given moment, time to time, but where vertically in the cloud and within the storm it's changing itself.
And what is the significance of this particular type of storm? For example, is there rotation sometimes associated with it, or just really bad rain and thunder, or what?
Yeah, I mean, at the most fundamental basis, these storms, what they're doing is redistributing energy across the Earth. So in the tropics, that's where the sun heats things up the most, and that's where you get a lot of convection, and that basically causes air at the surface that warms up to go up, and then it hits the top of the atmosphere, and that gets basically pushed poleward, and that big circulation is really just redistributing the imbalance of energy at the equator versus that at the poles. And so it's really, the Earth just is a big system that dynamically just wants to move air around to achieve a balance of temperature, but the sun prevents that from ever happening. So these deep storms are just all different types of storms. And what's really interesting about this is we're trying to look at different types of convective storms. So you can have anything from hurricanes, tornadoes, or just, a Wednesday afternoon on the beach in Florida in July where it rains every day at 4 p.m. So the idea here is that, being in space, because you get to orbit the whole planet, or at least north and south of a certain point because we're flying at an angle, you get to measure different types of storms and understand how the vertical motions within those storms are changing. And those will be different for each type of storms. And one of the big important impacts of that is we've never really had measurements of vertical motion from space. We can kind of estimate horizontal motions on how the winds move from looking at clouds and how they move around, but we don't really have the estimates of that vertical motion. So this is really one of the first measurements that will give us an idea of the precipitation in the cloud and how that mass of the cloud is being moved, and the storms are being moved around vertically in short periods of time.
We are speaking with Dr. Will McCarty. He's the manager of NASA's weather program. And just a detail question, if you have 3 satellites that you'll be launching to look at this from different angles or different properties from up above, where in orbit are they, such that doesn't the storm have to happen right under the satellites, or you miss most of the storms?
Right. So that's a good point. And that's really one of the main objectives for this mission. And it's a 2-year mission. And really, it's because you need about 2 years to be able to sample all the different areas under the cloud to come up with a good statistical representation of these storms. So a lot of work actually went on for how long does the mission really need to be? Because if you're only up there for 3 months, for example, you won't be able to sample everything. But there's really this magic sweet spot between 18 and 24 months where we think we'll be able to sample all these different types of storms in a statistically meaningful manner.
And what will the application be of this knowledge? Will it help?
So it really cross-cuts a lot of things. I mean, first order, because we've never had these measurements, these vertical motion measurements, all the weather models that really all of our forecasts depend on are been built around these assumptions, and these assumptions have never really been fully proven. So this will help us validate the assumptions in our model about how these vertical motions happen. And really, we know that those are sources of uncertainty and errors that really result in your forecast being wrong out a couple of days. So it'll really help us understand with observations, the physics in the models that we use that, that really feed into, our pockets and the weather forecasts that we look at, on a day-to-day basis.
And could this methodology help with, say, hurricanes? Because right now NOAA flies these airplanes horizontally through the hurricanes.
Yeah, absolutely. I mean, I think hurricanes, one of the big things to remember with any of these satellites we put into space is like NOAA flies aircraft through them, but they can only get so far out away from the coast. And then when they're out in the middle of the Atlantic or big storms in the Pacific that can affect Hawaii, where they don't do hurricane reconnaissance, satellites might be the only observations you can have. So that's actually, we've talked to people for a number of our missions, including INCUS at the Hurricane Center, for example, and the Joint Typhoon Warning Center and as well. They are so starved for data that they're really excited to get their hands on any data they can, because when you're in the middle of the ocean, it's not like you have somebody underneath it observing it. And
nothing in the existing fleet, the GOES satellites or any of these satellites up there, can do what you need to do with.
Right. So the GOES satellites can give you that two-dimensional picture, but they don't really see the structures within the clouds, which is what this microwave instrument does, this microwave radiometer. So we have a couple up there that can do that, but they're in lower orbit, so you really only get so many observations here and there. And when it comes to radars, we really only have one radar in space. And again, it's one by itself that gives you just that instantaneous view, not the 3 in a row that'll give you an idea of the motions underneath it.
And how will you get this? Well, how big are the satellites? What level of orbit will they be in? And how are you going to get them up there?
Yeah, so they're small sats. They're about the size of a mini fridge. That's kind of my rule of thumb. And they will be going up there on a launch no earlier than 2026. The launch contract had been awarded to Firefly Aerospace. It'll be launching out of Wallops. So for those in the DC area, it's actually a pretty short drive away to the peninsula to see the launch. And they'll be going up there, flying, I think, about 600 kilometers. Don't quote me on that. I don't have that one exactly written down. But flying around there and they all three will go up on the same rocket so that they can drift apart and really be in line, because they're going to the same plane, just so that they're overlapping the same storms.
And what is the source of the satellites themselves? Is this a NASA construction, or is that also a contractor building them for you?
It's a combination. It is being led by the principal investigator is Sue Vandenhever out of Colorado State University, and she really oversees the entire thing. At the project level, I am the science interface to NASA headquarters. The radars and the instruments are being built by the Jet Propulsion Laboratory, JPL, in California. The bus, the satellites themselves, is being built by Blue Canyon Technology, and then there are other contractors with smaller parts that fit in there as well.
Sounds exciting. Dr. Will McCarty is the manager of NASA's weather program. Thanks so much for joining me.
Happy to be here. This was great.
And we'll post this interview along with a link to more about the INCUS program at federalnewsnetwork.com/Federal Drive. Subscribe to the Federal Drive wherever you get your podcasts.